Hello, my name is Sylvain Allais from Université du Québec à Chicoutimi in Canada, and today I'm going to describe the main features of Synthia, a Java library that can be used to synthesize objects and data structures of various kinds. This presentation has been prepared for the demonstration track of the 44th International Conference on Software Engineering, ICSE 2022. Before going into the details of how Synthia works and what can be done with it, it might be worth taking a step back and asking under what circumstances one would need to generate objects. A typical software system, be it a single function, a larger library, or a full-fledged program, can coarsely be seen as a process that ingests input of some kind and transforms it to produce outputs of another kind. Suppose you want to run this software system, either because you want to test that it works correctly, or you want to demonstrate its operation to somebody, or you want to experimentally evaluate it by taking various measurements on its execution and the results it produces. Before you can do any of these things, you need inputs to give to your system. So where do you get them from? If the inputs accepted by your system are simple, like a number or maybe a character string, you can probably create them manually. You pick a few numbers, or you type a few strings, or maybe you have them generated randomly. But if these inputs become more complex, this manual approach won't scale for very long. What if the system requires a set of three-dimensional points that lie on the same plane, or a tree following a specific structure? Perhaps the system accepts as input other objects, such as instances of functions within your program. Or perhaps the system is interactive and expects a sequence of input events produced by the action of a user. If you happen to already have a set of pre-recorded real-world inputs, stored in the form of files or something else, good for you. You can simply use them. But what if you do not have any, or just not enough for your needs? Creating these inputs by hand is bound to be tiresome and error-prone, especially if you need lots of them. Besides, even if you do have real-world inputs, suppose you want to run a controlled experiment on the system. In such a case, you will likely want to vary one or more parameters that characterize the input to study their effect. For example, changing the length of a list, the number of elements in a set, the size of an XML document, etc. Doing so is hard when your inputs have already been collected. If you would like to run your system on, say, trees from 10 to 1000 elements, and some of these sizes are missing from your collection, well, too bad. In these situations, you may probably resort to a means of mechanically generating the desired objects or data structures. Pick the programming language of your choice and write a small script that creates whatever set of points, trees, or user events that is expected by your system. This solves many problems at the same time. First, you can produce as many instances of inputs as you want, provided that your script allows some variability in the things it generates. Second, you can parameterize your script so that you have control over the dimensions of the input you want to vary. Generate lists of various lengths, XML documents of various sizes, and so on. As a bonus, using a generator can even save space. Instead of storing the inputs, which may become an issue if they are large and need to be transferred to somebody else, you just store the script, which can regenerate them at any moment if necessary. This, in a nutshell, is the core business of the Synthia library, providing means to simplify the automated generation of various types of data structures and objects. In the current state of things, and barring a few exceptions, developers who want to generate inputs of some time have to start more or less from scratch every time. In contrast, since Synthia is a generic library that is reusable from one project to the next, time has been taken to design its architecture and cleanly implement repetitive functionalities that would hardly be worth the effort in a throwaway script meant to be used only once. Okay, enough talking. Let's now have a look at how Synthia is organized and start generating whatever you like. The core concept behind Synthia's operation is an interface called picker. Its basic task is to return, that is, pick, an object of given type T every time it is asked to. To this end, every class implementing the picker interface has a method called pick, which simply means give me another object. how this object is generated, if any, and according to what parameters or mechanism is completely left to each picker instance. By the same token, it is important to note that the use of a picker does not necessarily mean that the process is random. As we shall see, a picker for integers may return a pseudo-randomly generated number, but may also produce a sequence of outputs following a regular pattern or even a single constant value. Users are free to write their own classes implementing the picker interface. However, the Synthia library already provides built-in pickers for common types of objects. The first obvious thing that comes to our mind is numbers. Therefore, we are not surprised to see in the library the random integer and random float pickers, which respectively return an integer from a finite range and a uniformly selected floating point number in the unit interval. On their side, random Poisson and random Gaussian pick numbers according to their respective probability distribution, and random Boolean simulates a biased coin toss with a configurable probability. These first pickers allow us to introduce a nice feature of Synthia. Each picker class can be graphically represented as a square box with a corresponding pictogram describing its functionality. The usefulness of such a representation will be revealed later in this talk. As with any picker involving an element of randomness, the random pickers implement another interface called seedable. Seedable pickers have an additional method called setSeed, which accepts an integer. As its name implies, the number acts as the starting seed of a pseudo-random generation algorithm. This entails that all instances of a seedable picker, given the same seed, are guaranteed to generate the same output objects in the same order. Generating random numbers is no big deal, so let's continue our showcase with other built-in pickers that may seem less common. The playback picker acts as a form of tape recorder. It is given a list of objects to return and enumerates the next element of that list on each call to pick, looping back to the beginning once the list is exhausted. Thus, playback is an example of a stateful picker. The output it produces on a call to pick depends on the number of previous calls to the method. This means that the picker produces output values following a pattern, in this case, a repetition of the same sequence of objects over and over. By the way, note that playback can output arbitrary objects and not just numbers. A special type of playback is called constant, which always returns a single value. Any picker can be cloned and also put back into its initial state at any moment using two methods called duplicate and reset. A call to duplicate creates a new copy of the picker and places the new instance in the same internal state as the current state of the original. On its side, a call to reset restores the picker to its uniquely defined initial state. This means that successive calls to pick from this point on reproduce the same sequence of values as when the object was constructed. Note that this also applies to pickers that are based on pseudo-random generators. That is, duplicating a seedable picker will make the copy output the same values as the original from the point it is currently at in its sequence. A very important feature of Synthia, which makes the library very flexible, is the fact that a picker may be instantiated by passing to it one or more other pickers. Intuitively, this represents the fact that this picker must make a number of choices when producing an output object, and that these choices are based on the values produced by other pickers when they are queried. One of the simplest examples of such a picker is called tick. The tick picker starts with an arbitrary numerical value, which is then incremented by some amount on every subsequent call to pick. However, what is the starting value and by how much it is incremented every time is decided by querying two other picker instances. Thus, the graphical representation of the tick picker requires its box to be linked upstream to two other boxes, creating what we call a wiring diagram. In the illustration, S represents the picker that decides on the starting value, and delta is the picker that will tell how to increment the current value at each step. This is where things get interesting. Depending on what pickers are passed to an instance of tick, the sequence of numbers it produces may exhibit different patterns. If we pick the constant picker 0 for S and the constant picker 1 for delta, tick acts as a counter, producing the values 0, 1, 2, etc. If we replace s by a random integer in the interval 0 to 10, this time tick will still count, but will start from a randomly selected value between 0 and 10. If we put s back to 0, but replace delta by a playback picker, repeatedly enumerating the values 1 and 2, this time we get the sequence 0, 1, 3, 4, 6, 7, etc. Each value alternates between an increment of 1 and 2 with respect to the previous one. As you can suspect, this notion of wiring pickers to other pickers is very powerful. Just with the few pickers we have studied so far, we can generate numerical values following very different patterns. This distinctive feature also gives its name to the library. It follows the operation of analog synthesizer of the 1970s, which used signal generators and modules connected by patch cables. The output of one generator was used to modulate the output of another one, making it possible to produce various sounds by combining a small number of modules in different ways. As a matter of fact, the majority of the pickers inside Synthia are parameterized by other picker instances. Due to time constraints, I will not be able to describe all the built-in pickers in detail. Here's a quick presentation of some of the other classes worthy of mention. Freeze is another example of a parameterized picker. In its case, it asks for an object from another picker and then outputs this object every time its method pick is called. In effect, it works as if the original picker had been frozen and prevented from producing new outputs. Scramble asks for a variable number of values from another picker, shuffles their ordering, and places them back in that modified order. Pick element picks an element from a given set based on probabilities associated to each element. Pick list generates a list of elements of type T. The actual elements to be put in the list are provided by another picker, as is the size of the list, which is decided by a call to another picker producing a positive integer. Pick set and pick array do the same for sets and arrays respectively. Pick tree generates a tree by asking upstream pickers to obtain the nodes, deciding on the number of children of each node and the maximum depth of the tree. Some pickers are more geometric in nature and can serve as the basis for the generation of objects related to planes or space. Prism picker generates two-dimensional points by asking two pickers for the x and y coordinate of each point. Hypersphere picker also generates two-dimensional points, this time by asking for each point its radius and angle in polar coordinates. There also exist variants for an arbitrary number of dimensions. Other pickers can generate a triplet of numbers corresponding to the lengths of the size of a triangle, or a two-dimensional grid representing a polyomino whose size is given by asking another upstream picker. Yet some other pickers are geared towards generating objects whose ordering follows a complex relationship, which makes them appropriate to simulate some form of behavior. Markov chain, as its name implies, performs a walk in a Markov chain and, upon each transition, produces an object by asking the picker associated to the state it reaches. Behavior tree does the same for a path in a behavior tree. Grammar picker generates sequences of symbols picked from a set defined by a context-free grammar. One last picker that deserves some attention is nit, which takes other behavioral pickers as its input and interleaves the objects they produce in a single sequence of objects. It is a relatively complex picker, but you get the gist of how it works in the example shown here. The nit instance is given three instances of some other picker P, and you can see below each of them the objects that they produce on their respective calls to pick. P1 produces A, B, and C, P2 produces D, E, F, G, and so on. At the bottom right, you can see a possible output of the nit picker. Each successive call to pick returns the next object of one of the three pickers, resulting in an interleaved sequence as expected. For instance, if a Markov chain describes possible paths followed by visitors in a website, nit can be used to interleave pages visited by multiple users, thereby simulating what could be seen as a web server log. How do you create such pickers concretely? Here's an example of what you write to create a wiring diagram involving a few of the pickers we have seen so far. The box at the bottom is the hypersphere picker, which, as we have seen, generates points based on a circle radius and an angle. Other pickers connect to this one and determine how this radius and angle are selected for every point. Here, each is based on the generation of a random number. Take a moment to look at the code. You will see that there is, roughly, one instruction for each box of the diagram. If I run this program, I get a list of points, and if I drew these points, I would get plots like the one seen at the bottom of the screen. If I change the way the picker is wired to other picker upstream, I get other patterns of points, as you can see in this other example. Of course, producing points is relatively easy, but it shows again how objects following complex patterns can be created by plugging or wiring pickers together in a different way. Just for fun, here's a piece of code where a chain of pickers simulates the operation of an AM radio. And here's another one that generates a random scale-free graph simulating a website map, and then interleaves multiple random walks in this graph to generate a fake web server log. Note how in each case the chain is instantiated at a high level of abstraction and contains relatively few lines of code. As already mentioned, the main purpose of Synthia is to generate objects and data structures. However, the library was designed with the goal of being versatile. To this end, it collates under a uniform framework functionalities that are typically handled by distinct tools. Synthia supports automated test input shrinking, object mutation, provides a framework for monkey testing of reactive systems, and implements a rudimentary form of provenance tracking. Let's start with this latter feature. Every object produced by a chain of pickers, and even parts of an object, can be retraced to the precise upstream objects and values that contributed to its creation. Here's a code example where I create, again, a list of two-dimensional points in a different way. First, I instantiate the chain of pickers, and then I call pick to get a few lists of points. The interesting part is the last three lines. I designate a part of the first output list, namely its first element, and then ask Synthia to give me an explanation, which takes the form of a graph. This graph can then be rendered using GraphViz, for example, and produce a picture like the one shown here. This comes built in with Synthia, and as you can see, requires a single instruction, whatever complex the picker chain, the wiring diagram may be. Another feature is called input shrinking, similar to what can be done in implementations of the quick check framework. Here is an example where lists of integers are randomly generated until one is found that exhibits a fault in the underlying sorting algorithm. Pickers implementing an interface called shrinkable can automatically produce smaller values, and the repeated search for smaller and smaller values is automated by an object called assert. The way in which this shrinking proceeds is also special to Synthia, but you know why, you'll have to read the paper. Here, notice how a smaller example exhibiting the error is found after a first much larger instance has first triggered the fault. Synthia can also shrink sequences of actions sent to a reactive system. The sequence of actions is produced by generating random derivations of a grammar. This feature also comes built in, as we have seen. And once a failing sequence is found by another object called monkey, search for a smaller sequence proceeds automatically. Note that, as with any shrinking in Synthia, the shrunk input preserves the properties of the original. Hence here, any smaller sequence that is being tried is a subsequence of the original that is still a valid derivation of the grammar and not just any subsequence. This ends our tour of the main functionalities of the Synthia library. Of course, Synthia is not suitable for all situations, but I, for one, eat my own dog food and have used Synthia to produce synthetic data in almost all my recent research papers. For example, in the first publication, I used Synthia to generate Boolean formulas following a specific structure and used them to benchmark a test input generation algorithm I designed. In the second publication, Synthia has been used to generate sequences of events simulating the behavior of agents. In the third publication, I used Synthia to create fake web pages with injected layout faults in order to test a technique to fix GUI bugs. And the list goes on. There are many other publications I will not have time to mention in this presentation. There are many other things one can do with Synthia, and 20 minutes is way too short to show them all. I strongly encourage you to read the paper and even more so to peruse the documented code examples that are present in Synthia's repository in order to get a good feeling of what can be done with it. To sum it up, the main interest of the library is of course what you can do with it, but almost as much how you do it. The core of the library is made of a handful of simple abstract interfaces, which makes the design very flexible and versatile. Thank you for listening.